going to be dealing with the challenge of determining, you know, at least when we incorporate some more strategies and techniques into our learning, when is it appropriate to use integration by parts and when is it appropriate to use something else. So we have two strategies that we can choose from at this point. Really, actually, if you consider just general knowledge a strategy, which I guess it really wouldn't be, but if that's the case, then you might consider that like another approach that you could take. But I mean, if you know a rule that involves e to the x times the sine of x, then, you know, more power to you. I don't know a rule like that. So your choices at this point would be use substitution or integration by parts. So you would look at use substitution, for example. Can I define a u in such a way that its derivative would cancel the other part of the integral? So let's say I chose sine of x. Its derivative is not going to help me cancel e to the x. If I chose e to the x, its derivative is not going to help me cancel sine of x. Okay, so use substitution would not be an appropriate course of action here. Right, so at this point, because we're only limited to those two reasonable strategies, we would go with integration by parts. Right, there'll be other approaches that we incorporate down the line, but those, you know, battles for a different day. Anyway, we're going to define a u and a dv, and again, the u should be something that you start off with can differentiate, right? Ideally, it would make the situation simpler, right? It would make, you'd get a simpler function, so your subsequent integral would be simpler than what you started with, right? The dv should be something that you can integrate, but it should not make the integral any more complicated than you started off with, all right? Polynomials, again, I talked about this yesterday, just by increasing the power, you didn't make anything more complicated because it's still a power rule, right? In this case, this is one of those iffy situations because, well, you take the derivative or antiderivative of e to the x, the situation doesn't get easier or complicated, or more complicated. If you take the derivative or antiderivative of sine of x, same deal. Right, so it becomes a question of where would you want to place, we'll start with the e to the x. Well, personally, I would prefer to place that in the antiderivative part. And my rationale behind that is, yeah, it's going to be easy to take the derivative or the antiderivative of that, right? The sine of x, yeah, it's not difficult to take the antiderivative of that, right? But it's easier, even if it's ever so slightly, it is easier to find its derivative than its antiderivative, right? Even if it's just by a smidge, right? Tie goes to the derivative, right? So that's what we're looking for here. Just anything that would be more advantageous to us. Now, it is possible that this is a bad choice. If that's the case, then we'll do it again and switch them around. But you have to have an approach, you know, some consistent approach, and so that's the strategy that you want to have in mind, right? You want to make things easier through your derivative, and don't make things more complicated through the antiderivative, right? So we'll go through the process. Du equals cosine of x dx. Here we're integrating 1 dv and e to the x dx. So that's going to be v equals e to the x. All right, and again, we leave off the plus c until the very last step. All right, so the rule, the integral of u dv is equal to uv minus the integral of v du. In this case, it's e to the x sine of x dx is equal to uv, so e to the x plus e, sine of x, minus the integral of e to the x cosine x dx. All right. And this is the moment where you might start second guessing yourself, because you'll look at this and say, well, that didn't work, because this doesn't look any easier than what I started with. I couldn't find the antiderivative of e to the x sine of x, so So how the hell am I going to find the antiderivative of e to the x cosine of x? Perseverance. All right. That's the name of the game when it comes to, especially with trig-related integrals. So what you're going to have to do here is take it to the next level, or take it to the next step. We'll define a u as cosine of x, and dv again as e to the x dx. All right. After you see this in action, you'll see why it works the way it does, and then it'll become a little bit more obvious how I knew to take it another step. All right. So still the same idea. Take the derivative, take the antiderivative. We're looking at du equals negative sine x dx. Antiderivative of 1 dv is going to become v. Antiderivative of e to the x dx is e to the x. All right, so this is what I'm really just looking at. Again, it's the same rule. E to the x cosine of x dx is going to become, now it's my new u times v, so e to the x cosine x, minus the integral of v du. So that's going to become minus negative, so the two negatives will account for each other in a second, e to the x sine x dx. All right, so those two negatives will cancel to a positive. All right. So then it's like, there's so much going on. I don't know. I hate this. Let's start piecing it together, because that e to the x cosine of x integral equates to this. All right, so that whole thing can go in here. So I'm going to rewrite the whole shebang. Yes, it is a shebang. That's the technical definition of it. Superhero. Can't see more than 2 feet in front of me, but I hear everything. So e to the x sine of x dx is equal to the e to the x sine of x minus all of this stuff. All right. So e to the x cosine of x plus the integral of e to the x sine of x dx. All right, I'm going to simplify a little bit more, rewriting the whole thing again. All right, it doesn't really seem necessarily important at first why I would write the whole thing every single time, especially the left-hand side. Couldn't I just write the right-hand side? But it's in this last step that hopefully it becomes clear why I was writing the whole thing. Because you notice that you have like terms on both sides of the equation. I have an integral of e to the x sine x dx on the left-hand side, and a negative e to the x sine of x dx on the right-hand side. So what I can do, add the integral of e to the x sine x dx, both sides of the equation. And so we'll get two of them. So if I want to get the integral e to the x sine of x dx all by itself, my final step, well, still have a little teensy tiny step after that, but the last major step would be to multiply both sides by 1/2 or divide by 2, same deal. All right, so multiply both sides by 1/2. and you get final answer of e to the x sine x dx as an integral equals, you can distribute the 1/2 if you want. I'm not gonna. 1/2 e to the x sine x minus 6. Oh, that's funny. I mean, only to me though. You can tell by the lack of laughing. There it is. Plus c. All right, so multiply both sides by 1/2. I rewrote it, and then I just tacked on the plus c at the end. That required a knuckle crack at the end. Look at that. All right, so when it comes to integration by parts, again, the first challenge is recognizing that it is integration by parts, but I guess that's not really a challenge for today, because the exit ticket problem is going to be an integration by parts problem, so you don't have to diagnose. But you want to decide what the u is going to be and what the dv is going to be. So in this case, geez, look at that. That was a poor quality u. I'm looking for a u that when I differentiate will become simpler, and a dv that when I anti-differentiate, first off, it should be something that I can anti-differentiate, but it should also not make the situation any more complicated. Okay? So if I take, for example, the x and make that the dv, it won't get any more complicated when I anti-differentiate. It's still a power function. But I'm looking at that secant squared, right? Because taking the derivative of that is not going to make things simpler, right? It would involve chain rule. But taking the antiderivative of that would be great, because we know that secant squared of x is the derivative of what? Tangent. All right. So just right off the bat, I can say that I'm taking the antiderivative of 1 dv and the antiderivative of secant squared x dx, and we get v equals tan x. Now, they're both still trig functions, but I think just by the look of it, you could all at least kind of come to grips with the fact that tangent has to be a little bit simpler, or it might seem to be a little bit simpler than secant squared. All right. X would be my u, or u would be my x. Take the derivative of that. I'm looking at du equals dx. All right. So again, the rule. The integral u dv is equal to uv minus the integral of v du. All right, and so that's x secant squared x dx is equal to the product of u and v, x tan x, minus the integral of v du. All right, so the du is equal to dx. That's great. All right, so tan x dx. All right, now you get to this part, and you would say, all right, it's either a fact or it's something that I'll have to integrate using a technique that we've covered. All right, if you happen to know what the antiderivative of tangent of x is, because it's a parent function, that's fair game. Any kind of parent function, if you happen to know its antiderivative, you don't have to reinvent the wheel. All right, so if you knew that the antiderivative of tangent x is x ln x minus x, oh, actually, no, sorry. That's ln of x. Oof, that wasn't even close. Tangent of x is the natural log of secant x. It wasn't even close. Well, there was an ln in there. So it's like this much right instead of being this much wrong. So anyway, you would have to most likely use another technique. All right, so would that technique be integration by parts? Not necessarily. All right, so what we can do is pull off the integral of tangent x dx and just take a look at that independently. All right. so tangent, sine over cosine. All right. So then the question would be, can I identify a u? So u substitution, I'll just make a note, u substitution. Can I identify a u in such a way that when I take its derivative will help to cancel out the other part of the integral? Well, if I call u sine, that'll help cancel out the cosine. If I let u equal cosine, it'll help cancel out the sine. So I can go either way with it. It's just a question of, well, if I go one way, am I going to get painted into a corner? All right, so I'll let you decide. Which way should I go? Cosine x? Probably because I already kind of gave it away by saying ln. So you knew it would be the... So du equals, this is actually the correct choice. So experience on my end.
How did everyone else know it was cosine?
Yeah. I saw two minuses and made a plus.
It would have to cancel with the dx.
Yeah. If we cancel the sine x dx, if you did cosine x, because then the derivative of that is equal sine x.
Right. Yeah, that's the nice aspect of this choice, or the nice consequence anyway, is that when you take the derivative, it gives you the clean cancellation right across the board. All right. Now let's actually look at the choice of sine. Let's say we took u equals sine of x. Du would be equal to cosine x dx. All right. So if I replace u with, sine x with u, that would go away. Then dx would be the same as du over cosine of x if I wanted to swap that out. But really, there's no way to do a clean cancellation here. Right? In fact, all I would be doing is making the cosine of x into a cosine squared of x with this choice. All right. Fortunately, there's only two possibilities when you're making your selection for u in this situation. So you go down one path and it turns out to be the wrong path, you'll be fine, because it's very quick to see. All right, well, that wasn't right. Let me try something else. All right. So in this case, if just looking at the blue, I just need to get rid of that negative sign. So negative du would be equal to sine x dx. So I can swap out this whole thing with just a negative du. I'm still hung up on my my x ln x minus x blunder. It's in my head now. -1 over u du. Sometimes we see what we want to see, I guess. All right, so antiderivative of -1 over u is what? Negative ln of u. All right, I'm not going to put the plus c here because I know it's very easy to lose sight of this, but this is still just part of our solution. We still have the other part up above, the x tan x. So I'll have to put it all together in a sec. We're only focusing on this piece right now. All right, so this is negative ln of cosine x. All right, so that's an acceptable way of representing your integral. All right, but you might say, oh, wait a minute, I thought you said that it was the natural log of secant. Well, or exponent jumps over the log like a frog, right? As Miss Hamilton would say. She likes frogs for some reason. Cosine to the negative first power is the same as what? Secant. All right. Also, it's a pretty good reason why you might, with trig functions, avoid the -1 power notation when you're dealing with inverse functions. instead of writing it as cosine -1 of x, you might choose to write arc cosine, because in this context, you know, it's the entire cosine function raised to a power of -1. That means reciprocal, not inverse. All right, so that's kind of why whenever I have a choice in the matter, I tend to default to the arc notation. So anyway, you could go with either one, actually any one of these three possibilities to include here. You may opt to go with the ln of cosine, the negative ln of cosine, because it'll cancel with the negative sign here. There's a bunch of different ways you can go. So anyway, we're looking at, let me just bring it in, final answer, x secant squared x dx is equal to x tan x. I could say plus ln of cosine x plus c, or I could say minus ln of secant x. Yep, I said what I was going to write. Or I might say, I can't think of a circumstance in which I would want to write this, but I could say minus the natural log of cosine to the negative first. That's another possibility. I guess the one thing I wouldn't say is x ln x minus x plus c, because that would just be idiotic.
Before you do all of the u substitution, are you allowed to move the negative sign into the integral so then you don't have to make the du?
Yes, you can.
Okay.
Yeah. That would have been a good thing to do. I missed that. Yeah.
Does the integral sign and then -1 over u du, does the du just mean take the antiderivative?
Yeah. At least until the next unit where we learn what its true meaning is.
So it could be du or dx?
Yeah, exactly. Just indicating what the variable is. All right. So that's kind of it. I mean, the two juicy types of integration by parts questions are the cases where you have to integrate by parts multiple times, or you integrate by parts and then you have to do something else afterwards, like maybe in this case, like use substitution. All right. So down the line, when we learn more techniques, it could be integration by parts plus one of those new techniques. All right. So that's when it starts getting interesting. All right. Slash fun.
The step from -1 over u du to negative ln absolute u,
Mm-hmm.
how did that happen?
That is a rule. Yeah. The derivative of the natural log of u is 1 over u times du dx. But
Is that like in the packet somewhere?
it should be on page uno.
Can we go over question 8?
8 on page 9.
Please.
Absolutely. Ooh, an arc sign. There's some questions where, as long as you know that it's a integration by parts question, you're at least confident in the fact that you can get started on it, because something like arc sine of 3x, you don't know the antiderivative of it. So that has to be my u. And the only thing that's left would be dx. The one issue with that is if you don't know the rules for finding derivatives of arc functions, so inverse trig functions, that could be your first and only step in the solution to the problem. So that could be a problem. But well, actually, no, that's not fair. You could definitely get v equals x.
Or plus c.
And yeah, just throw a plus c there. I've had that happen before.
Or you can just like guess something like kind of similar and then just
Yeah.
keep going.
Something that you know is in the neighborhood of the right answer, and then just throw a plus c on it.
You get like me, I would say, this is definitely gonna be wrong. 1 over radical x squared, 1 minus x squared.
That's correct if it were arcsine of arcsine of just x. So if you had just,
Oh wait, so that was really close.
that was very close.
Heyo.
Yeah. So it's there. It's just
But like, if I did that and then continued throughout the rest of the problem.
half a point deduction.
Oh.
Yeah.
Okay, cool.
Now, if you were absurdly wrong, like you just went way off the rails with that 2-point conceptual error, but then after that, I mean, you did everything correct based off of that error. You wouldn't forfeit any other points. Right? So that's good news. Now, just for the record, the derivative of the arcsine of u, some function u, is equal to u prime over the square root of 1 minus u squared. Okay. Or 1 over the square root of 1 minus u squared times du dx, either way. But that's your rule, and the cosine, our cosine is just a negation of that, if that comes up. So we're looking at 3 over the square root of 1 minus 9x squared and a dx. All right, so again, the rule, u dv equals uv minus the integral of v du. So in this case, it's arc sine 3x dx is equal to the uv, so x arc sine 3x minus the integral of the v and the du multiplied. So this is where it's going to get a little juicier. Okay. But the good news is it doesn't look like it's going to involve parts in the second part of the problem. All right, so we have to tackle this guy. So again, you're diagnosing the situation. You're asking yourself, based on the 2 significant techniques that we've learned, aside from just fact-based information, is it u sub or is it parts? Well, it's u sub if you could define a u in such a way that when you take its derivative, it'll help cancel out the other part of the integral. Right? So the beefy part of this integral is the 1 minus 9x squared. What's the derivative of 1 minus 9x squared? Negative 18x. All right, that's just a constant multiple away from being 3x. So that means that this is a u sub situation with my u being equal to 1 minus 9x squared. So du is going to be equal to negative 18x dx. Now, I don't want negative 18x, I want 3x. So I'm going to divide that by negative 6. So negative 1 over 6 du is going to be equal to 3x dx. All right, so a little bit of housekeeping. You can incorporate the negative like I didn't do in the last one if you want, or you can just leave the negative alone. It doesn't really make a difference. I already kind of boxed off the integral, so I'm just going to work with it as is. So I'll do it in red. We're going to have a negative 1 over 6 du, replacing my 3x dx, over the square root of u. That's the same as saying, and you could skip steps obviously, in this, for the simple algebra, negative 1/6 u to the negative 1/2 du. So now I'll just use the reverse of the power rule. So u to the positive 1/2. So I'm taking negative 1/6 and dividing it by 1/2, which is the same as multiplying it by 2. So negative 2/3. I'm sorry, negative 2/6, negative 1/3. All right, and then swap back the u, which again is a 1 minus 9x squared. So this is going to become negative 1/3 times 1 minus 9x squared to the positive 1/2. And again, don't lose sight of what we're doing here. That's this part. So my final answer is going to be the x arc sine 3x. So I'll just do a big old equal sign here. X arc sine 3x plus, because I get two negatives, 1/3. Just make it look a little nicer. I'm going to make a radical. It's a more handsome expression. And then tack on the plus c at the very end. Otherwise, you got plus c's everywhere. It's going to be a nightmare. Or actually, I wouldn't say that. That's an over-exaggeration, or just an exaggeration. Just if you include plus c's everywhere, then there's a chance you might lose one along the way, and it might cause a little trouble. All right. So again, another multi-step problem where you have the integration by parts to start off, and then after that, you have to do something else. That something else, in this case, just like the last one, was use substitution. Anything else? We have left time. I want to just leave the last 10 minutes for the exit ticket. So I could do more. What's that?
How long do you expect it to take?
10 minutes. You want to start now?
Yeah.
Yeah.
You don't want to do another one again? Okay.